Welcome to Ask and Learn.
For this problem on the topic of equilibrium of rigid bodies, we are told that a pole of a given length is acted upon by a force as shown, where we are given the magnitude of the force. The pole is held at point A by a ball and socket joint and by two cables BD and BE. If we are given a value for A, we want to determine the tension in each cable as well as the reaction at point A. So here we have a free body diagram, and we have 5 unknowns with 6 equations of equilibrium, but equilibrium is maintained. Now the sum of moments about the pole MAC is equal to 0. The vector RB is equal to 3J as we've drawn it in our diagram, and RC is equal to 6J. So these are the positions of B and C relative to their origin. The other vectors, we have firstly CF is given in vector notation by minus 3I minus 6J plus 2K. And the vector has magnitude of 7 meters. The vector BD is 1.5 I minus 3J minus 3K, and this vector has magnitude BD is equal to 4.5 meters. Vector BE is 1.5 along the x direction minus 3 along the y direction plus 3 along the k direction, and this vector has magnitude of 4.5 meters. So the length of BE is 4.5 meters. Now the force P that we've labeled in the diagram is equal to the magnitude of P multiplied by the vector CF over C, the magnitude of CE. Magnitude of CF rather. So that is the direction of CF. So this is equal to the magnitude of P over 7 in the direction of CF minus 3I minus 6J plus 2K. The tension of BD, TBD, is equal to the magnitude of the tension in the direction of BD. So that's the vector BD divided by the magnitude of BD. So this is TBD divided by 4.5 times the vector 1.5 I minus 3J minus 3K. And we can actually simplify this, and this becomes TBD over 3 into I minus 2J minus 2K. Now the tension TBE is equal to the magnitude TBE in the direction of BE, which is the vector BE over the length of BE, which becomes TBD, or TBE rather, TBE over 3 into I minus 2J plus 2K. Now, with all our information, we can finally take the sum of the moments about A. And we know the sum of the moments about point A must equal to 0. So the sum of the moments about point A is RB crossed with TBD plus the vector RB crossed with tension TBE plus RC crossed with vector P, and this must equal to 0. So now we'll use the method of cofactors to solve this cross product. So I, J, and K So if we enter our vectors in here, that's 0, 3, 0, crossed with 1, minus 2, RB cross TBD, and this is multiplied by TBD over 3, plus the cross product 0, 3, 0, which is RB, crossed with TBE, which is 1, minus 2, 2, times TBE over 3, plus RC cross P, which is 0, 6, 0, minus 3, minus 6, and 2 times P over 7 must give us 0. So let's look at the I coefficients, and we get from the I coefficients that minus 2 TBD plus 2 TBE plus 12 over 7 times P must equal to 0. We'll call this equation 1. From the J coefficients, we get minus TBD minus TBE plus 18 over 7 times P is equal to 0. And we'll call this equation 2. Now, if we add these two equations, equation 1 and equation 2, or actually we take equation 1 and add it to twice equation 2, we get minus 4TBD plus 48 over 7 times P is equal to 0, which means we get an expression for TBD in terms of P. So TBD is equal to 12 over 7 times P. And if we go back into equation 2, we get minus 12 over 7 P minus TBE plus 18 over 7 P is equal to 0, which means now we can find TBE in terms of P. So TBE is equal to 6 over 7 times P. But we are given the magnitude of P. We are told P is equal to 445 newtons. And therefore, we find TBD to be 780 newtons, and TBE, these are from the expressions above, is 390 newtons. So those are our two tensions as required. Now we have the tensions. We want to find the reaction at A. So if we take the sum of all the forces, we know the forces acting on this pole at equilibrium must equal to 0. That means that the tension of BD plus the tension TBE plus P plus the reaction A must equal to 0. Now let's take I coefficients for our forces, and we get 780 over 3 plus 390 over 3 minus 455 over 7 times 3 plus the x component of the reaction AX is equal to 0. And so simplifying, we get AX to be 195 newtons. So here we have the x component of the reaction. Now let's take J coefficients, and we get minus 780 over 3 times 2 minus 390 over 3 times 2 minus 455 over 7 times 6 plus the y component of the reaction AY must equal to 0. And so similarly, we find the y component of the reaction AY to be 1170 newtons. Now finally, if we take the coefficient of K, we get minus 780 over 3 times 2 plus 390 over 3 times 2 plus 455 divided by 7 times 2 plus the z component of the reaction AZ must equal to 0. And again, we solve for the one unknown, and we get AZ, the z component of the reaction, to be positive 130 newtons. And therefore, we can find the vector reaction A in unit vector notation to be minus 195 newtons times unit vector I plus 1170 newtons times unit vector J plus 130 newtons times unit vector K. And that's our reaction vector.